Okay, good morning again, and welcome to. Do you guys hear me well? Because I hear myself, but for some reason.
No, we hear you good.
Okay, for some reason it's really doesn't look like it's working the way it was before in the past. Anyway, I prepared the activity for you, but I refrained from doing it because when I posted it on Canvas, it flunked the accessibility basically test big time. So I cannot really share that one because I have to make sure that that is accessible to everybody. So what I'm going to do is actually I'm going to post it for you guys later on After Effects, all of the other things, and makes it accessible to everybody. So that's one thing. The other thing also, we'll have a simple project basically because we're going to be exploring today the Kepler's laws basically and learn how the planets move, more or less, at least in terms of Newton's perspective. And we will be learning in that the planets that are bound to the sun and any satellite that is bound to the Earth is going to stay in what is called an elliptical path, okay? And we will build ellipses basically in your home. All you need is a ruler and a piece of paper and a pencil and also a protractor to make sure that, I don't need even that. You just need a ruler, you need a string, and you need 2 thumbtacks basically to hold the thing in place. And you're going to build your own ellipse. And then after you do that, you're going to measure what is called the major axis from end to end, basically on the fat side with the ruler. And from the thin side, you're going to measure also from end to end. And you're going to do some simple algebra, basically, to find the properties of the ellipse, which gives you an idea of how planets move around the sun and how actually satellites move around the Earth, or how moons move around other planets, for example. I mean, we have only one moon, so for our case, it's... I mean, for example, if you take Jupiter or Saturn, they have dozens and dozens of moons, okay? So those gives you an idea of things that are bound to other objects move. I mean, there are other objects that are not bound, so we're not going to explore them in this activity. So we're going to work on that activity, prepare it for you guys, and you do it, and you're going to submit it online. Okay, so for some reason, we have less than half the class today. And any questions before I start? No? Okay. So let me share with you where we were left off last time, if I can find it. Okay. So we were talking about the conservation of energy, and that in processes where there is no dissipation, for example, of energy, like for example, when you don't have friction, or in processes when there is no input. By the way, if I get disconnected for some reason, it happened yesterday for me in another class, please do not leave, okay? Because I may have to restart my router or go on my phone or something just to make sure, because the internet yesterday was not working well in my place. Anyway, in a process that does not have friction, for example, in a process that does not have an input of energy, such as, for example, a motor, an engine, that has other external processes that is adding energy to the system. We'll see later on when we do the electricity, there are some electrical ways also of adding energy to a system, external ways. The energy is conserved, okay? The energy is conserved even in those cases when there is friction and when there is actually an input of energy. When taken in that larger context, in a sense that if I can tally those dissipative processes where the energy is actually dissipated, or processes where the energy is actually injected into the system. If I can tally those, the whole thing is actually conserved. The universe, the entire energy, amount of energy in the universe is conserved. It does not, there is no place for the energy to basically disappear or appear from, okay? Energy always transforms from one form to the other. In the special case of a mechanical system, such as, for example, in this picture, what I have a string attached to it, a mass, okay? If I lift the string, if I yank it with that thing, I'm giving it potential energy. If If I take this object sitting in here, for example, and if I lift it up, I'm giving it potential energy. Now it has potential energy because it's the higher level. How do I know that? If I let go of it, it's going to convert that energy into energy of motion, which is the kinetic energy. So that is a process in here. You have potential energy. In this case, it's a gravitational potential energy. Do I have a spring in here? The only spring I can see is the one for this one. So again, I can build, if I have it, I had it backward. I can build energy by just pulling on it. If I let go of it, it's going to move back in here. Again, potential energy, kinetic energy, they are actually, they interchange. There is an exchange between them. Again, you can lift an object, for example, using kinetic motion and then gain potential energy back again. In the case of the spring mass system, you have the spring that is, if you pull it one way and attach to it a mass, it's going to oscillate. It's going to go back and forth, back and forth, back and forth. While it's completely stretched, it stops, then comes back. And then it's going to compress a spring. At some point, it's going to be moving super fast. While the spring now is completely unstretched, the mass will continue moving and compress the spring now. When it compresses it, the spring will compress to a smaller amount, and then at that point, the mass will stop, and then the spring will push it back now until it's completely relaxed, the spring, but at that time, the mass will be moving. So it's going to continue stretching the spring, I'm sorry. And at that point, it's going to stop. So there is, while it's stopping, while it's changing its motion, there is actually no kinetic energy whatsoever. Remember, the kinetic energy is proportional to the velocity squared. So it's 1/2 mass times velocity squared. When the mass is at its max, away from the position of equilibrium, at that point, it stopped because it wants to come back. At that point, it has no kinetic energy. But at that point, the spring is completely stretched, is fully stretched. So the potential energy at that point is maximum. It's at its max, while there is no kinetic energy. And then when the mass moves back to the equilibrium, at that point, the string is completely unstretched, is at its relaxed place. At that point, I don't have potential energy, but the mass is moving super fast. I have complete 100%. I probably will, it makes it easy if I draw a diagram in here. Is there a tool in here to draw in this thing in here? Okay, can I draw in here? No. Let me see if I can get, it's easier to do it in here. Let me stop sharing the screen to illustrate my point in here, okay? Because you really have to have an understanding of how that thing works in here. So let me share the screen now. Share. Okay, where is my pen? So let me go back to the mass spring system. Okay, Sarah has probably a link there that might be useful, but let's talk about it quickly in here, if I can get my draw thing in here. So I have spring in here, with it a mass. If I don't pull the mass out of its equilibrium, let's say, for example, this is sitting in equilibrium. Since it's in equilibrium, there is no problem. At this point, things are no problem. There is no. So this is unstretched. This is equilibrium. When I disturb it out of its equilibrium, when I take the mass and move it at some point, then the spring is stretched. I built potential energy in the spring at that point. I'm still holding the mass. So the mass is not moving. So at that point, there is no kinetic energy because it's not moving, but there is potential energy because the spring is stretched. If I let go of it, the mass will be pulled by the spring and will come back at that point back to the equilibrium, in which case the spring is completely unstretched. So the potential energy is zero, but the mass is not going to stop there. The mass has actually motion, has velocity. So its kinetic energy is not zero at that point. It's going to actually continue moving by inertia, actually. It's going to continue moving in the opposite direction. It's going to compress the spring now because of that kinetic energy. Because remember, the kinetic energy is equal to 1/2 mass times velocity squared. Since it's moving, it has kinetic energy. At that point, it's going to compress the spring. So the spring now will compress to a new location. So the spring will be this much compressed by this much. Okay. Now at that point, the mass stops. Since the mass stops, the kinetic energy is equal to 0, and the potential energy is not equal to 0. Why? Because the spring now is fully compressed, which means it needs to relax that energy. So it's going to push now on the mass that is standing still at that point because it stopped. So it's going to push on it until it's completely relaxed back to this position. The spring now is relaxed. I don't have potential energy anymore, but I have built kinetic energy now all of a sudden, the one that I lost in the compression stage. So at that point, I have kinetic energy, but the potential energy is 0. Now, the inertia will make it so that the mass will continue moving forward downward, converting that kinetic energy to potential energy again until at some point it stops, in which case I lose all of the kinetic energy and regain all of the potential energy. And this process will stay forever, technically, unless, of course, we have friction. And that is why this thing will stop. Because in every stage of the process, the mass spring system will lose some of that energy to the friction. So it's, yes, there is an exchange of energy between potential and kinetic, but at some point, every stage, of the process, we lose part of the total energy to friction. So the system has less and less energy to convert to potential and kinetic, less and less energy to move, and at some point it loses this completely, and the system comes to a stop because, again, we have friction. So this is an ideal situation. This is not, this is not the situation that is probably going to be. I mean, in practice, you will have the mass will stop. Okay, friction will come into play. Same thing with this thing in here. So if we devise, for example, a way of converting kinetic energy into potential energy, gravitational potential energy, we saw gravitational potential energy is proportional to the weight times h. Okay, times the height. So in that case, it's still, if there is a way for me to up and down, then we can actually also see the similar process. In the same token, also, friction will make it so that the process will end at some point. Okay, so that's the friction for you. Any questions about these things? No? So, so the work done in breaking a moving car to a stop is the force of friction times the distance with which it stops. If the initial, I'm sorry. Okay. What is the chat in here? If the initial speed of the car is doubled, the stopping distance is actually less, about the same, twice. Mathematically, the friction is really complicated subject, so the correct answer is it's somewhere in between, actually. Between the because if you come in faster, you're going to need more distance to stop, but not necessarily double. So the math behind it is a little bit complicated, but again, the friction is the one that is going to slow it down as much as it's the one that is really going to also expedite the process. Okay, the math is a little bit complicated. I mean, if it's predictable, then we will have a problem with we will have the friction also as being a conservative force, which is not the case. Does this make a little bit sense for you, Masada?
Yes, it does.
Okay, very good. The friction, usually there is a word for it they use in physics, okay? They call it bad boy of physics. The minute friction comes in, the whole thing goes hayward, okay? So, but it is really a useful force in some senses, but it's an undesirable force in another instances, okay? I mean, without friction, we cannot move. Okay. Principle of a machine. So a machine machines, and that's one of the things we talked the other day about the incline being a machine, simple machine. Machines do not provide work, do not add additional work. Okay, technically, the work input must be equal to the work output. And I just mentioned a little bit about this friction thing. Usually, this is not an exactly equality; it's almost equal. The output is usually less than the input. Okay, in an ideal machine, they will be equal. Okay. But in a practical situation, any machine, whether the lever, whether the what is it, the screw also, whether the wedge, whether the incline, all of this simple machine, the pulley, for example, all of these simple machines, and there are 6 simple machines. They are they basically the output work usually is a little less. Okay, but that's basically some. Because of the friction again. In order to find the work, you multiply force times distance equal to force times distance in the output. Okay. What is that famous saying? Was it, I think, Euclides who said that that give me a lever and a point basically of support, and I will lift the world for you. Okay, because again, since we know the mass of the world, for example, if we take the Earth, this is how much weight it weighs. And if you give me a lever, then I need to find this distance times the mass of the Earth. All I need is just a huge distance in here to compensate for my little effort to lift the world for you. Okay, so if this is the so-called effort, and this is the load, and this is the arm distance for the load, and this is actually the arm distance for the your effort. So you have L times your effort is equal to, this case, the load itself times this distance D, and you can find the L needed. If all you can afford is 10 newtons, for example, and you have 1,000 newtons in here, so you need the ratio of this distance to that one to be 10. Okay, so if you need to lift 1,000, and you know that it has to be at a 10 meters from there, and all you can afford is 100 newtons, so you need to multiply this by 100, not 1,000. 100 times 100 is the same thing as 10 times 1,000, which is 10,000 each. Okay, so that's what this algebra is all about, basically. That's what the math is all about. As long as you can get a lever that is long enough, you can lift whatever you like. Okay, Earth if you want. So, okay, there was some concepts we thrown in the beginning of this chapter, namely the concept of momentum and kinetic energy. There is a difference between them. Kinetic energy is a scalar, is a number. It's always in joules, 12 joules, 15 joules, 150 joules. It's always positive, though. The difference in kinetic energy may be negative. You may start with a kinetic energy and end up with no kinetic energy. So 0 minus something is going to be always negative. But in the quantity by itself, and at the given point, it's always greater than 0. Because again, it's 1/2 mass times velocity squared. Mass is positive, 1/2 is positive, and velocity squared, it's always going to be positive. Whereas the momentum is m times v, and v is a vector. So the momentum actually is a vector. It has direction. Okay, that's the big difference with them. Kinetic energy does not. Both of them, they depend on the velocity, though. Both of them are related to v somehow. One of them is the square of the velocity, namely the speed, and the other one is related to the velocity vector itself, which is speed and direction. Okay. Okay, that's a key word in here. I know when we talk about the conservation of energy, some people think that we belong to a specific group of activists. No, the conservation of energy in sense in here that it doesn't change. Delta E stands for the energy and delta stands for the change, is equal to 0. That is what this means. Conservation of energy means the energy does not change. It stays the same. Delta means change, okay? That's what delta stands for. Capital delta. change. No change. That's what that expression says. No change in energy, okay? It remains the same. If you calculate the energy initially, if we take, for example, the mass and spring system, when we pulled it up, when we pulled it down and let go of, before we let go of it, we know the kinetic energy is zero. We know the potential energy is equal to some finite value. Let's say, for example, it's 100 joules. At any instant later on, it doesn't matter where the spring is at and the mass is at, whether it's fully stretched, whether not stretched at all, well, fully compressed, or anywhere in between them. If you add the kinetic plus potential, you're going to end up with 100 joules, no matter what that is. That is exactly what the language is. It has nothing to do with a specific group of activists going in the oceans and doing stuff and whatever that is, okay? So that's exactly what it means. It has no political meanings whatsoever. So the law of conservation, in the absence of external work, input or output, the input such as an engine, for example, is inputting energy in your system. The car, for example, has an engine, which is a chemical reaction that is adding energy to the overall system, okay? Or an output, for example, taking from your energy, draining energy out of your system, such as friction, for example, or air resistance, or whatever the process that you're dealing with. In this case, the energy of the system remains unchanged, okay? Because all you're dealing with are what is called conservative forces and the kinetic energy. In this case, for example, you're dealing with the weight, or you're dealing with the spring, or you're dealing with specific force that does not change things. So in this case, it's still, the energy remains the same. Does this make sense? The key word in here is absence of external work, because friction either does work or have work done against it, depending on the direction, its direction and that of the direction of motion. The engine either does work or having work done against it, for example, trying to use the engine to brake, for example, okay? So that's some of the things that you can do in here in this case. Energy cannot be created or destroyed. Actually, this statement is true even in the case of the presence of external mechanisms of gaining or losing energy. And that is because if you take the entire universe from edge to edge, there is no known way of creating energy or destroying energy. Somebody might say, okay, how about this expression that we will learn later on about it? Well, then in that context, the mass actually is another form of energy. For a moment, ignore that expression for right now. This is Einstein equivalence between mass and energy. So in that case, in that context, mass actually is energy too. So there is a way for you, if you wish, to convert mass into energy. But in this case, if both of them are the same thing, so there is no question about that. Okay, so ignore this expression for right now. We're going to see it in the future, okay? We're going to get into it toward the end of this course, okay? Okay, consider a system of, what is it? A bow and arrow. In drawing the bow, we do work on the system and give it potential energy. When the bowstring is released, most of the potential energy is transferred to the arrow as kinetic energy and some as heat to the bow. So basically, at some point, when you pull on it, that's where the energy is. It takes energy from your muscles, from your body to do that much energy and give it to the initial energy. Now, you have a system that has been disturbed out of its equilibrium because you have now the bow stretched, and if you let go of it, so the spring will push back to its equilibrium position, converting its energy back into the arrow in this case. It's going to go traveling with the kinetic energy. Plus, of course, in every single process, even during the pulling stage where you're building up your energy in the system, there is this dissipative processes in terms of heat and friction and things like that. So this is the example they're talking about. Suppose the potential energy of drone is 50 joules and the kinetic energy of the shot is 40 joules, then the energy is not conserved, or 10 joules go to warming the bow, or 10 joules go to warming the target, or 10 joules is mysteriously missing. So in this case, it must be in some sort of heat, okay? That's basically how you're... In other words, you have to account for the missing energy no matter what. But this is 10 missing mysteriously, that's not acceptable, okay? A is not correct because in a sense we have an imbalance in terms of the energy. We have 50 and 40 in here, okay? Sometimes I have difficulty watching the chat. I see it flashing, but I can't see anything in here because I'm in the sharing mode, okay? Okay, very good. So, okay, in the discussion later on, all of you are awake? In the discussion after this chapter, so the answer is going to be either you tell me it's C, or you're going to say the question of the day, 10 joules goes to the warming of the, to go to warming the target, okay? Is everybody following me in here?
Yes.
Yes.
Okay, very good. So if you come later on and ask, okay, what was the question of the day? This is it. I'm not going to be able to repeat it later on because it defeats the purpose. The whole thing is I want you guys to be participating in the class, even those who are not able to make it live because of work and things like that, or other classes or whatever is going on because we're online. I'm not going to. I'm going to ask you basically refer you back to the to this live session. So go to the live session. You should be able to discover what the question was and the correct answer to it. So you're welcome to put just C, okay? The answer is going to be C. Okay, that's fine. That's good enough. Or if you want to be verbose, 10 joules to warming the target, okay? If you want to put the words in it, okay? Because we have a 50 and 40, and the mystery in here is where is this conservation? It's not. There is an imbalance of energy. So where did that energy go? It's mostly going to, I'm sorry, did I say C? It's B. Because we don't know what the target is. Oops. They didn't mention anything about the target in here, did they? So the correct answer is B, B, B. So if somebody watched in here and reached that point and put the correct answer C, they're thrown off track. Okay, let me fix that, okay, quickly. So the correct answer is B, okay? Does this make sense, Sarah? Sarah Faulkner? I know we have a couple of Sarahs in this class. Yes?
Yes.
Okay, very good, okay? Because they didn't say anything about the target or anything like that, okay? So you cannot invent something that is not in part of the question. That's why some of these questions actually are tricky in a sense, because it may make sense to you, but then you look at the question again and you see that there is something. That's why some of these questions are not really necessarily physics questions, but they're testing your ability to be paying attention to the question itself or not, okay? So a machine, a device for multiplying force or changing the direction of the force. So no machine can put out more energy than it puts in. That's one of the basic laws that we will learn later on in thermodynamics and the laws of heat and energy. Create energy, it can only transfer or transform the energy. So basically, change the direction of the force. For example, in the case of the pulley, instead of actually going up and pulling on something, you can actually pull it from down and then it's going to rise, okay? So that's what the case of the pulley is. Or change the value of the force. For example, in the example of the lever, instead of picking up 1,000 newtons, for example, 1,000 pounds, for example, and you can't pick it up. You can't physically do it. It's too much for you to lift it. So what you do, you use a lever. In this case, you use less force. But in this case, that distance matters. Compensates for it, and you're done. And you will see a person, I mean, not necessarily strong, lifting a whole engine of a car with the proper tools, okay? With the proper machines, okay? By himself. But if you ask him directly, go and lift the engine, he cannot, or she cannot. So that's basically that's why the simple machines, and they're all mechanical machines. Here is the example of the lever. I already talked about that. Oops. So in this case, you have a force, which is a load, usually, which is very heavy, okay? and the distance from here that is going to travel, or here, both of them are actually proportional. The distance of travel in this case is small. You lift it, but you don't lift it that high. So if you ask me to lift an elephant, I can always lift an elephant for you, but not that high probably. I mean, like for example, a mouse, which I can lift a little higher than this one. So that's the thing with this. And this is the effort. This is how much force you really need to put in the system. You need to travel a long way. That's why if for people who have, for example, garages with those mechanical things, you will find yourself pulling on a pulley so much and building up a lot of chain underneath your feet so that the door lifts slightly, okay, or the engine lifts slightly. If some of you have had experience with those doors, the old mechanical doors, not the ones with remote controls nowadays, you will understand what this means, okay? You will understand how these things work. Okay, an ideal pulley system, a woman lifts a 100 Newton crate by pulling a rope downward with a force of 25 Newtons. And why did they pick up a woman? I don't know. Anybody, okay? Child, for that matter. 25 Newton. For every 1 meter length of rope, she pulls downward the crate how much? Because, remember, for every 1 meter length of rope, so she needs to pull 1 meter for the crate to rise how much? The crate will rise in X amount. Let's do the algebra quickly in here. So the crate will rise in X amount, which I don't know, times the weight of the crate, which is 100 Newton. And she uses 1 meter for the rope, and she can only have 25 Newtons. So cancel the Newton with the Newton, and this is meter, of course. So it's going to be X should be from this algebra 25 times 1 divided by 100, which is 25 divided by 100, which is 25, 0.25 meters, or the correct answer is C. Okay? Does this make sense? Yes? By the way, in my announcement, when I sent it to you guys the other day about when we're going to be meeting, we're changing the time and all of that, I said from 8:30 to 9:45, and that was wrong because we're supposed to be here till 9:55. I mean, an hour and 25 minutes. Although probably if we finish early, we're going to leave early. So that was the second question for you guys to answer today. So the correct answer for the second question is 0.25 meters or 25 centimeters, however you like to call it. Okay? So there are 2 questions for you today. Yes?
Got it.
Okay, so make sure you note these things. You don't have to wait for the video upload to go and answer these things. You just go there and put your answer. Of course, you cannot see anybody's answer unless you post your own. And then after that, you cannot edit it. So there were 2 questions today, and those are the only 2 questions. And so far, at least. The first one was answer B, and the second one is 25 centimeters or 0.25 meters, whichever you like, okay? I don't remember what letter this question was.
Professor, I have a quick question. So
Yes.
for every lecture that we have a discussion post? Because I know
Yes.
that we have one for chapter 3, and then this is chapter also 3, or?
This is going to be chapter 3 and 4, because again,
Okay.
if it's going to be chapter 3 and we don't go to chapter 4, it's going to be chapter 3 part 2. Okay.
Okay. So just to clarify, for every lecture that we have answers for chapter 3, and then we have questions to answer for chapter 3 and 4.
For this one, yes, because next week you might end up only with chapter 5. Okay. So it doesn't, depending on the session of the day. Okay, every session we will have a discussion participation. Now, there will be sessions with no participation, but most of them will have participation toward the end, okay?
Oh, okay. So we have questions to answer for Tuesdays and today's.
Yes, and
Got
then the other thing also is, I'm not going to tell you how many questions or what the question is. So if it defeats the purpose if I do that, so you're going to make sure that you're following us, you're doing your live stuff, and basically if you cannot come live, you're going to go. And this is only fair to you guys too, who are here live too, so that the other people don't basically take a ride for free there, and at the end probably, okay?
Okay, thank you.
Okay, so today there was 2 questions. So the first one is part B. And the second one in this case is, or the friction to the bow, or the second one is heat to the bow, that is, or the second one in here is either 25 centimeters. Question C, answer C, it's the same thing. I'd rather see the number though, and or 0.25 meters as we did the algebra in here. Okay. This shows an understanding that there is actually no gain or loss of energy. This is actually energy. This is work. This is how much work is done in lifting that this is the output energy, if you wish. This is the output work. This is the input energy, how much the girl is putting in there, how much the woman is actually working in this case. She put 25 newtons over 1 meter, basically dispensing of 25 joules. The other one only can also do 25 joules. And that's why you have 25 centimeters, which is 0.25 meters times 100, which is also 25 joules. So all she did is spend 25 joules, so she can only get out of it 25 joules. That's why the 100 Newton rose only 25 centimeters, did not rise a whole meter, okay? So she cannot, the simple machine in this case, which is a pulley, cannot give you more energy in this process. It cannot basically help you lift 100 Newtons 1 meter, which end up with being 100 joules in that case. And then, but she only spent 25 joules. So where is that 75 joules coming from if the crate actually rises a whole meter, okay? The crate only rises 25 centimeters to tell you that she only spent 25 joules, so she only can get 25 joules out of this whole thing. And that's why 100 Newton can only go 25 centimeters or 0.25 meters to make it so that that is how much you gain from it. Do you guys understand? This is why this is critical. This is why understanding this question is really the essence of a lot of the ideas that we discussed this so far, okay?
Sounds good.
Okay, so a question in here in terms of the efficiency. How efficient is a specific engine or a machine? It's really in this expression, and this is where a little bit of algebra is required when we're doing math in here. I know that some math is, I think what is it, math 150 or something. I don't remember exactly which math is required, but if it's required at all. But doing a ratio in this case is not hard. The work done over the energy used times 100%, because that's going to be a fraction. That's going to be a number, okay? That is what the efficiency is. That is if I have one simple machine. But I can combine simple machines and make out of them more complicated machines. That's what a car is, actually. It's a combination of several machines. You have all kinds of I'm not talking about the electrical part of it, but the mechanical part of it is really a combination of several machines. So in this case, you ask what is the efficiency of the overall machines as they are combined. Then in this case, there is a formula for it. The efficiency for a combined machine is that it's the product of the simple machines they made it up. So each one of them has its own efficiency. And because they're all fractions, so the combined simple machine will end up with less efficiency than that of each and every one of the individual machines, simple machines that it's made up of. Okay, a certain machine is 30% efficient. This means that the machine will convert 30% of the energy input to useful work. Okay, 70% of the machine is wasted. That's what it means, okay? 70% of the input is useful, 30% no. As strange as it may sound, both have the above. No, that's contradiction. That's nonsense. They cannot be the same, both of them, okay? Or none of the above. The correct answer in this case is A. This is not a question that requires your prompt later on, okay? So this is easy. This is so easy that even I can do this. Sources of energy. The main source of energy in on Earth is actually the sun. The sun is where we get most of our energy from on a day-to-day basis. The plants get energy from the sun. They do whatever their photosynthesis is. Don't ask me a lot about biology because I have no idea how things work. But at the end, they produce food for us and the other animals. And basically, we take that food and make it into energy, and we exercise and we basically move around. Either we take the plants directly, the food from the plants directly, or the food indirectly from other animals that eat those plants. That's basically one way of doing it. The other way also, fossil fuel is actually coming also from the energy because that's deposited over a long period of time. So our carbon-based energy, that is basically our civilization, is also dependent on from the sun, basically energy that was converted from sun. There are some energies, I mean, also whether this is true for oil or basically for other kinds of basically fossils, basically that we use them for our day-to-day basically energy. For example, the Hoover Dam, for example, actually it also uses the properties of the sun because again the water is going through a cycle because of the fact that the entire weather is actually affected by the sun. Most of the energy of the Earth is coming from the sun. There are some very, very small amounts of energy that don't come from the sun. And one of them is actually the heat inside the earth. And that is actually coming from another process. It's called the radioactive processes. And those are actually not related to the sun. They are actually from different processes. So radioactivity, for example, is not coming from the sun. That is nothing has to do with the sun. Most of the other energy, though, is coming from the sun. So sunlight evaporates water, water falls as rain flows in rivers and goes into basically the Hoover Dam and turn the turbines, and the turbines basically spin inside the magnets, and that will generate electricity using something called Faraday law. And solar energy can transfer into electricity, and solar energy indirectly produces wind that can turn turbines. So basically, even the wind turbines that you see them while you're driving, for example, somewhere, you are also coming from the sun. So the sun is our source of energy in this case, okay, for the most part. Okay, these are some of the other sources of energy. So the dry rock turns steam and power into turbines. So again, that's our similar processes of making energies. Solar power. We have photovoltaic panels. Photovoltaic panels, basically what they do is the light hits the cell. The cell, because they have specific frequency, the electrons are basically expelled from their atoms and they start moving, and now you have electricity since charges start moving. And then we talked about Hoover Dam and also the wind turbines, and there is a bio-based fuels. Okay, so those are some of the cells that we talk about. If you go to Walmart, you can buy actually a chemical cell. Okay, this is one of them. Okay, actually I got it from Amazon, this one. So again, they are chemical based in this case, and then so there is all kinds of sources of energy. This is basically the hydrogen creation. Basically, what you do in this case, you dissociate the atom of the water, H2O, and break it down into H and 2 and O. H2 and O2, I'm sorry. When we did this experiment, I remember in high school, the professor told us this is going to be very dangerous because we created hydrogen and it's highly explosive and we have to be very careful and everything. And there was a lot of excitement, I remember that day, because we were expecting a big boom when he lights it up, and it went really like a puff because there was not too much hydrogen produced. And you remember, I mean, you can imagine the audience there, everybody was laughing because we expected something, big explosion. But of course he was right. I mean, that was on a very small scale because we didn't produce a lot of hydrogen to begin with. Okay. So this is some of the processes in the photovoltaic cells. This is some of the pictures for that and how to convert energy from the sun using things that we probably are going to discover down the road. And that is why Einstein actually won his Nobel Prize, not because of relativity or other things, it's because of his work in this field. How an electron is extracted from an atom and basically made into moving, and that's how the cells work, okay? So this is chapter 3 for you. We still have time to do some work on chapter 4. So let me share that screen with you, unless you guys have any question. So in this chapter 4, it's basically the universal law of gravity. That's what we're going to discover. Newton in 1666 basically discovered this expression, discovered this law, while the legend has it that he was sitting under a tree and then an apple fell on his head, and then he said F equals to G times M1 M2 over R squared. That is not how it happened, okay? That's not how it happened. According to some accounts, he did not deny them, he did not confirm them. At least one of his close friends, he mentioned something about him basically thinking about the apple, and now the actual, how should I say, the closer to the truth version of it is the following. After the pandemic hit London, and everybody was sent home from the college, basically where he was going, just like you guys. Just we are in a similar situation. So one of you probably is already coming up with great laws that save humanity. Hopefully, finds a solution to this COVID thing. Anyway, he was sent home, and he was at that point has already discovered. He was a student still. I mean, in his early 20s, he has discovered the 3 laws that we talked about them. Law number 1. Namely that the universe, if it's made up of a single object or non-interacting objects, and this object can be isolated, then if these objects are under no net forces, then this object will keep their velocity in the same value in the same direction. That's law number 1. Law number 2 says that if an object is actually under a net forces, then it's going to accelerate or change velocity, both in direction or magnitude or both, and in such a way that this change is proportional to the force that caused this change and inversely proportional to the inertia of the object. Then law number 3, he said that if objects now do interact, they do so if one exerts a force on the second exerts a force that is equal in magnitude in opposite direction. So those were his 3 laws that he discovered at that time. Before him, at that point, Kepler came up with 3 laws, and all of the 3 laws of Kepler were based on observation, what you see actually, not based on theory, because his laws, Newton's laws, are actually extrapolation of observation and made them into statements that became laws. Mr. Kepler's laws basically looked at the planets, looked at the data from Tycho Brahe, who was with him, who actually asked him to come and work with him, and looked at already at the Copernicus models that Copernicus has came up with, and basically came up with 3 laws. The first law says that planets actually, and this was true even with Copernicus, do not revolve around the Earth, as we already know from Copernicus. They revolve around the sun, and he said that they don't revolve in circular paths. There was a big deal about that because the church believed, and people believed actually, let's not just blame the church for that, even commoners, basically everybody, believed that heavens are perfect, okay? Earth is not perfect because we humans sinned and made it so that it is not perfect. And the only perfect shape that is out there must be a circle, because a circle has no rough edges, if you wish. It's as smooth as it can get. So the heavens are not messed up with the humans, so they must be circles. Everything that has to be there in circles. Look at the moon, for example. It's circular shape, basically. That's how the argument was. And as a matter of fact, they argued that the Earth was, the objects were going around the Earth in circular paths. And where Copernicus also changed his view that the Earth is not the center of the solar system, but the sun is, he kept that idea of circular paths, that everything revolves around the sun in circular paths. Mr. Kepler, when he looked at the data, he didn't like that at all. It does not fit that picture. He said that they're actually ellipses. They're not circular paths. And the sun, of course, because it's an ellipse has what is called 2 focal points. The sun, he said, must be in one of those 2 focal points. So the sun sits in one of the 2 focal points. The other focal point is empty. There is only one object in the focal point. And objects go in a not circular paths, but elliptical paths. That was law number 1. Law number 2 says that as these objects move around the sun, as these planets move around the sun, when they're closer, they speed up. But then when they're further away, they slow down. In such a way, the rate with which they sweep the area around the planet, around the sun, is constant. So that was law number 2. It did not take him long to come up with these 2 laws, but it took him a very, very long time to come up with the 3rd law. And the 3rd law has to do how long for a planet to go around the sun versus how far it is from the sun. There is a simple mathematical expression between the ratio of those 2 quantities, namely the time squared. It goes 1 year, for example, for the Earth. For Mars, it's almost 2 years for how long it takes for a planet to go around the sun, and how far it is from the sun. And that is the cube of the distance. He found that ratio to be perfectly constant. The time squared, or the period squared, over the distance cubed. So that ratio is constant. So that was his laws, and he discovered them way before, of course, Newton came onto the picture. So almost half a century before he came into the picture. So when Mr. Newton was basically in isolation in the pandemic, he wanted to explain, or actually he was asked, I forgot who, I think Haley or somebody else, I don't remember actually the exact name. Anyway, somebody asked him about the explaining Kepler's laws, 3 laws, using your 3 laws of mechanics, because these are objects moving in space. So here is where the apple comes into the picture. He theorized first of all, he said, forget about the planets. All I'm going to do is focus on the moon. If I understand the moon, I understand everything else. He said that maybe the reason why the moon is tethered to the Earth and not leaving it and it basically going around it, because at that time Kepler's law say that the moon actually revolves around the Earth, then, and we can see that day in, day out actually, then if that moon is under the same force of attraction of an apple, for example, then if I can find the relation between the 2, then I'm in good shape. So that's where the apple came into play. And indeed, he found that relationship between how the moon is attracted toward the Earth and how the apple is attracted to Earth. And he said, this must not be only true for the Earth and the moon. This must be true for everything out there, including all the planets around the sun. Hence the word universal. He came up with an argument based on the moon and the apple, and he made it into something that governed everything else, okay? And he was right to almost tremendous accuracy, to a point that when a comet was seen later on, people started basically speculating, okay, does it obey Newton's laws? So when the math was applied to it, they predicted it's going to come back from Newton's laws in 76 years from the day. Sure enough, almost a century later, almost within a few days, it came back. So Newton's theory is actually correct, because it predicted something that was not in Kepler's observations. That's one thing. And also, toward the end or the middle of the 19th century, 18 something, 2 mathematicians independently, one in actually France and one in England, they predicted the existence of planet Neptune after by accident we discovered Uranus. Uranus, it was not known at that time as one of the planets. So we discovered the 2 predicted that there is another planet based on the Newton's laws, and they tell us exactly where we should go and point and look. At that time, the British Observatory, when they saw the 2 studies coming independently, they pointed to that direction where the 2 mathematicians independently and unknowing of the other ones basically said to point, and sure enough, they found Neptune. That's how Neptune was discovered, purely based on math developed from Newton's laws. Of course, there was a big problem at that time, and that was Mercury. Mercury could not be explained with these laws. Mercury faltered. Mercury was a problem, and it took the genius of Albert Einstein to explain Mercury. And that's why the mechanics of Mr. Newton is limited. Everything we learned up to this point, there is a limitation to it. The problem, for example, in the case of the solar system, falters exactly with Mercury. Everything else works beautifully and matched to an unbelievable accuracy, okay? We'll discover that this law is inversely proportional to the distance. the further the object, the weaker this force is between gravitational force, basically. Talk about weight and weightlessness, and I think I mentioned about the going in business together about this one a long time ago, and so far nobody wanted to go in business with me on that. Do you guys remember that proposal that I asked you guys to?
Yeah, that was funny.
Okay. Nobody so far wants to go in business with me? Okay.
That's the weight loss one, right?
Yes. Okay. Okay. So I'm still hoping that one of you probably will take me on my offer. Okay. Okay. And then the universal gravitation, basically, we'll talk about projectile motion, which is an example of a two-dimensional motion. You throw an object, it moves one way, and also in the other direction. So it moves horizontally and vertically in the same time. In the vertical direction, it's going to be accelerated toward the Earth. In the horizontal direction, there is no acceleration, so it's going to maintain that velocity. We'll discover the concept of range, and we'll discover the concept of basically, what is it, the height and the angle of basically the projectile. We'll talk about that later on. Talk about circular orbits, circular satellite orbits. They're not, like I said, exactly circular, but they're very, very close. There is a concept that you're going to be doing in the activity I proposed in the beginning, and that is concept called eccentricity. If the eccentricity is exactly, what is it, I mean, there is a limit between 0 and 1 where it's completely circle and when it's completely flat. So we're going to find that quantity. And we'll talk about the elliptical paths. That's what the project is going to be. And we'll talk about the escape velocity. The escape velocity is what is the minimum velocity with which you can escape the pull of gravity. Of course, you cannot escape the pull of any gravity. You will learn that because of that 1 over distance squared. No matter how far you are always under the influence of all the objects in the universe. But of course, this drops rapidly with 1 over distance squared. So ultimately, you can say that they are gone. So for all practical purposes, there is a velocity for the Earth. It's 11.2 kilometers for every second, where if you reach that velocity, you're going to escape the pull of the Earth. And that's basically the facts for the Earth. For Mars, it's a little less. For when Matt Damon was stuck on that planet, by the way, this picture was inspired from Mars because you see the flow of the, this is actually in the Sahara Desert in Africa. This is, was it? I think, yes. There is the sand itself looks like it's water and basically flowing. So in this case, there is not a waterfall, a sandfall, okay? So on Mars, for example, the escape velocity is a lot less than that of the Earth. So Matt Damon was not dealing with the 11.2 kilometers per second, but he was doing about something like 5 or 6 kilometers per second, which is a lot less than that of the Earth. So on the Moon, it's even less. Okay, on other planets, for example, on Jupiter, it's even higher. For the Sun, it's actually even bigger. So far, we have only one object that has actually escaped the pull of the Sun, and it's still out there in the Oort cloud. Even the Oort cloud itself, which is loosely connected to the Sun, is made up of a lot of objects that are still bound to the Sun. Oort cloud is a huge, basically, region of space that surrounds the Sun. And we will talk about that when we talk about the solar system, basically, and you will discover that it has some properties that are unique to it and make it outside of the... So I gave you, basically, in a nutshell, the entire chapter, in a sense. So even if we don't finish it, I assume that you guys can finish these things. So this is, in a nutshell, the whole thing, okay? So again, this, as I said about it, it's more of a legend than an actually true story. Okay, and if you don't believe me, just go tomorrow. Go to an orchard and sit under an apple tree and see if you're going to discover anything. I think you will end up with a headache more than actually discovering anything. At least that's my theory. Okay, hopefully you guys prove me wrong. So this is what I said earlier, that people believed in the idea of circular paths and that the heavens actually, and I don't want to have the whole blame actually on the church, but basically other people also have that idea, even from Greek philosophy. They had that thinking that the heavens are actually because of their circular paths and all of that. And Ptolemy actually in the beginning of the century toward not the around the what is it, around the time of just before Jesus or around that time basically, he came up with the idea because there was a big problem. When you look at the circular paths, they fit more or less, okay? You can predict where objects are moving. Here is where the problem was for Ptolemy that he wanted to understand. Mars, if you look at it tonight, I don't know if Mars is visible tonight or not, I don't have my astronomy data before me, but if you look at it, for example, a specific point of time, all of the objects are moving in space in one direction. That's one thing, because of the rotation of the Earth, okay? That's no problem. And they arise in the east and they set in the west. That's no problem. And the planets, the reason why they're called planets is because they jump from place to place. They are not like the stars, for example. They have a weird motion. We'll talk about that down the road. Mars, though, was a problem because at some points it's moving like everybody else in the sky, but then it's going to move backward and then move forward again. So Mars had that problem, which was really a big problem. People later on, when they looked at Venus, also Venus did the same thing, but not as bad as Mars does it. And then, now we know, it's not actually Mars and Venus that do that. All of the planets do that, okay? But before that, Ptolemy wanted to understand that. So he said, okay, here is the Earth. It's the center of the... can I get into the drawing again in here? I like that drawing too. Here he said the Earth. As the objects are moving around it in circular paths, okay? Mars, he said, it's actually moving in a circular path around its own circular path. So at some points it's moving forward like everybody else, like this guy, like Jupiter, moving in this direction, but some other times it's moving in a circular path and it's moving backward. So that's why he explained it's called the retrograde. That's why it was explained. But it's moving in a circle inside a circle. But then that model did not fit perfectly with Mars, so he said, okay, maybe other people actually suggested it's moving actually in a circle inside a big circle, which goes in a bigger circle. So the picture gets a little bit messy and complicated. And when actually Venus also was discovered to having that behavior, that explanation also was put forward for Venus. The picture got very, very complicated to try to explain these motions. That's why actually Copernicus also believed in the circular paths, but he solved to some extent this issue with circle within circle within circle. Okay, so that's basically how this facts in order to basically, Mr. Ptolemy basically his observation was used to predict the calendar. It was used to predict, for example, when and that's actually something that was commissioned by the church to actually do predictions. When are we going to celebrate the Christmas, for example, next year? When is the religious holidays, basically? When is Easter, for example? Okay, so they want to know those dates in the future, and at some point, according to the calendar, if you follow it, Easter all of a sudden is happening in the middle of the summer. Things were completely out of whack. Things are completely out of shape. That's why actually Copernicus was hired by the church to fix the calendar, that's all. In doing so, he said actually the Earth is not the center of everything, it's the sun is, and the Earth and everybody else is moving actually in this circle, in these circular paths, okay? So that's how the picture that emerged from Mr. Copernicus' observations, okay? He stuck to that circle idea though. And he was having an issue big time with basically he didn't believe there was some flaws in his theory. He wanted to basically come up with, and I think we talked about that last time. Basically, one of the things that he struggled with is the concept, okay, and that's why he didn't publish his book until almost he was about to die. And okay, if a bird is on a tree and there is a worm on the ground, and if the Earth is moving, and it has to be moving super fast according to this model, then how come a bird can fly down and catch the worm? Of course, he didn't know how to answer that. It was really a struggle for him. So he didn't believe in the data that he was looking at, although the data was suggesting that the Earth is not the center of the solar system, and actually the sun is. And it took his genius, as a matter of fact, because for commoners like anybody else, I mean, for me, for example, when I look at the objects moving in the sky, it takes a lot of imagination to really envision that actually it's the other way around. Okay, now we take it for granted because we have a lot of things that come around to explain it, and documents and movies and pictures and books and teachers and things like that. So we come to believe it not because of our observations, but because of basically what was instilled to us day in, day out. But actually, it takes a lot of genius and math actually to show that observations to actually see it the other way around. And that's exactly what Copernicus did. So that's why his approach was called the Copernican revolution, and the word revolution was used not basically out of context. It is really true. And he's right, of course, the observation support that, including, for example, the problem that I mentioned earlier for Mars and other objects. So that's the only explanation for it if the sun actually is in the center of the solar system. So he explained that picture beautifully. But of course, Galileo came in later on and saved the day, and saved the day for a lot of reasons. First of all, he saved the day for the concept of why the bird catches a worm. It has to do with the concept of inertia. Yes, when it flies off of a tree, the tree moved because of the earth is moving. The worm is moving because of the earth is moving. The wind also is moving because of the earth is moving. And so is the bird because it has also that velocity in that direction with the earth and everybody else. So there is no reason for it to be left behind. So it's going to go down and catch its worm. So that's inertia explains that problem. Not only that, but he also was able to convert the telescope that was actually used by as a toy to actually observe other objects and actually see that there are other objects that revolve around the other objects. He looked at Jupiter and he saw the moons of Jupiter going around it. Okay, so in other words, this is basically the picture at that point, and the picture has changed by the time that Mr. Newton was looking at this object, at this theory, basically. And in his approach in trying to understand things, he said that, and this is actually, you can do this experiment. I mean, you don't have to do this. You don't have to wait for Newton to explain that to you. Take a, we used to do this. I mean, I forgot the word for it, what it's called. But you have a piece of cloth, you have a rock, and then you spin it around, okay? Or you take actually a string and you attach to it a mass and you spin it. The only reason for the rock to stay in orbit is if it's moving fast enough. Case in point, if you cut the string, the rock will fly off, or the object will fly off, okay? The same thing, the reason why the moon is actually going around the earth as if there is an imaginary rope holding it to the earth, and that imaginary rope is provided by the force of gravity. So that's basically how we explain this one. As it's going to move in one direction, it falls just enough to stay in orbit. It falls just enough to stay in orbit, okay? And the law that he arrived to, there's a lot of basically arguments he had to make for this one. It did not take him long to come to it, by the way. He came up with it very quickly. It took him 4 years to publish his work, though, because there was another mathematical problem that he had to answer, and that he ended up basically inventing calculus for that. So at some point, it seems like Mr. Newton was doing everything by himself. Nobody else was doing anything. So in this law, this is the law of universal gravitation, basically. This is the force of two objects of mass 1 and mass 2 at a distance d from one another. So imagine that I have mass 1 in here, and I have mass 2 in here, and this is the distance between them, d. The mass is in kilograms. So the mass of the first one in kilogram, the mass of the second one is in kilogram, and the distance is in meters. So we use this expression to find how much force they attract one another. This is a force of attraction, okay? G here, that's why he actually had to compare between the moon and the apple, because he knows the rate at which the apple falls to the ground. That Mr. Galileo has computed it with a value of G equals to 9.8 meter per second or meter per second squared. So that's Mr. Galileo has already found little g for it. In order for him to reconcile this g with the little g that big man G has found, he had to basically compare the apple with the Earth, and basically that's how we came up with this value for this G, which is 6.67 times 10 to the negative 11, which is very, very tiny number, 0.0000000, basically 10 zeros followed by 6, okay? So it's a very tiny number, and that's to make things work for the apple and also make things work for the moon, because we know how long the moon goes around the Earth once. It takes a lunar month, which is almost a solar month also. It's almost 30 days when it goes around the Earth once. So that's basically how long it takes for the moon to go around the Earth. He knows also the distance between the Earth and the moon. That was calculated a long time by the Greeks, so he knows that distance. So he knows D from there. He also knows the mass of the Earth. At that point, you can actually estimate the mass of the moon from there, and you can find, you don't actually need the mass of the moon. It cancels out in the expressions. Okay? So in this case, you can find, and since you know the period, you can find a lot of the math in there, and you make sure that the G makes sense. So the G that he brought in here, this big constant G, was just to make things work for him, for the moon and the apple. And since it works for the moon and the apple, he said that this big G must work for everything. So if this big G is just a constant, it's a number to make the units work, because this is in Newton, the mass is in kilogram, the other mass is in kilogram, and the D is in meter. So the units must work. So you need to introduce G there. And also he knows that Mr. Galileo has calculated G, little g, for the apple to be that one. So if I want to apply this one for the apple, this is the mass of the apple times the G. The mass of the apple, as I said, or that of the moon cancels. So big G times the mass of the Earth divided by the radius of the Earth squared must be equal to this tiny G. So he had to invent big G to work that way. So that's really how things happen. That's how much work he needed to do. But that was, like I said, was not his biggest headache. His biggest headache was, why did he have to take the diameter, the distance, I'm sorry, as that of the radius of the Earth and not actually the distance? Because when I drop an object, it falls from the height I drop it just to this distance. In this case, it's less than 25 centimeters. So why not 25 centimeters? Why the whole radius of the Earth? So for that, he ended up inventing calculus, as I said. So the universal Newton of law, Newton discovered that gravity is universal. Every mass pulls on every other mass. Okay, that's basically his discoveries. Newton's most celebrated synthesis is earthly and heavenly laws. Okay, so that's really what he did. Okay, that's really the biggest law he discovered, bigger than the other three laws that he discovered, because this one he arrived to it. The other is weightlessness. I'm still waiting for takers. Mass and distance has nothing to do with it, and the others, so they're not related to this question. Okay. This is what this law says: the bigger the mass, or this mass, the stronger the force. He argued basically the apple, the only reason the apple falls to the Earth is because it's attracted toward the Earth. But if I am warm living on the Earth, on the apple, and looking down, I see the Earth actually rushing to fall on the apple. From his vantage point, the apple is not moving, but the Earth is moving towards him. So that's basically some of the arguments you have to make in there. The distance is the square of the distance. If you double the distance, the force shrinks by fourth. If you double the masses, the fourth quadrupled. But if you double one of the masses, the fourth doubles only. This G is constant. This G doesn't change. As a matter of fact, G is a property of the universe we live in. Had G become a little bit bigger, had G was only 10 decimal points after the 10 values after the decimal point, not 11, the universe probably would not have had a chance to form. It would have collapsed immediately on itself. So this G is what keeps the universe the way it is. Actually, if this G was actually a little bit smaller than that, not just 11 values after a decimal point, I mean 10 zeros plus a value, but actually another increment in there, the universe would have flown apart a long time ago and would not be here sitting talking with one another. Your atoms would not have had a chance to basically form. So again, this G is just what the doctor ordered for our universe to be the way it is. Okay. So this is a property of our universe. It's a constant. It doesn't change. Okay. Even Einstein's equations have this value of G in them. Okay, one of the objectives of modern physics is trying to answer this question: why G it is what it is, why it's this big or this small, if you like to call it that way. Okay, again, the intensity of the force is proportional to the square of the distance. The square law is similar to what you do, for example, when you spray paint. The closer it is, the more intense, the further it is, the weaker it's going to drop, and it's going to go through a bigger area, basically. And this phenomenon is actually true also, for example, light, a candle. If you put a candle close to you, it lit more room. But if you move away, it has to spread throughout an entire room. So it's going to be less and less, its effect is going to be less and less on your book, for example. If you're holding the book and bring it closer to it, there is more light hitting the book. But if you move away, you're not going to see much of the, it's going to have less effect because the same entire light has spread throughout a big room. If you move very far away, you're probably going not to have any effect whatsoever from this one. So the inverse square law here is a very important concept. And again, it has to do with our universe because we live in this three-dimensional universe and we have this perception that things spread in a sphere, okay? Same thing with your cell phone. Sometimes when you're close to from the tower, you have 4 bars. When you are moving away from the signal from the tower, you will have less and less bars because the same signal from the tower is spreading through an entire sphere, basically. So this concept is used actually in telecommunications a lot. This is what the inverse law says. Right at the edge, the force is at its max. But of course, it's going to be bigger if you approach the center. But it's going to be less and less because of the fact that you're going to be closer from the, you'll have less and less mass in your effect, okay? So, but it's going to drop. It's never going to go to zero though. Even if the distance is 1,000,000 meters, yes, you're going to divide by 1,000,000 squared, but then that's going to be 0.000, basically 16 digits or 12 digits, 12 zeros before the digit appears, or 11 zeros before the digit appears. But it's not zero. It's always a finite value, no matter how far you are. That's my point initially. That's why you see here in this edge, it never touches the x-axis. It's not going to be zero. The force is not going to be zero, but rather approaches zero. That's the word that we use, approaches zero, okay, as you move away and away from it. Like I said, in the beginning, I know I gave you an overview of the entire chapter and I discussed a lot of these ideas already. So it's just details in here. So I'm going to rely on you that you guys will go home and basically finish these things. And if you have questions, please let me know because we're going to move on past this chapter, okay? So a force of gravity between two plates depends on their mass and distance. And that's the correct answer. That's the third question for you guys, okay?
Okay.
Okay, so basically, so the third question the answer to it either A, or if you choose, mass and distance. However you like to put it, it's up to you, okay? So there were 3 questions today. The first question was B, the second question was 25 centimeters if you like, or 0.25 meters. And the last question is A, or mass and distance, okay? So we needed to cover some stuff in here for this thing in here. So for you guys, it's going to be quick, okay? So you can go and put the answers. For the others, they really have to go through the entire thing. That's why we like to spread them throughout the entire chapter to make sure we're covering enough stuff in here. So if 2 masses, I'm going to end there in 2 minutes, okay? Unless you guys have any questions. If the masses of 2 planets are each somehow doubled, the force. So if we double the mass 1 and double the mass 2, so we're multiplying the first one by 2 and the second one by 2, 2 times 2 is 4. So the correct answer should be quadruples. Of course, if we double only one of the masses, the whole force only doubles. That's what that law is saying. Okay? If the mass of the planet is somehow doubled, so in this case, it doubles only. One of the planets doubles, okay? The force of gravity between it and the neighboring planet doubles only. Same thing, if somehow you can cut the planet in half and basically separate it, and now you want to have the effect of this planet with the other planet, the third planet, then in this case, you shrunk the mass by half, then that half will only be halved, okay? So again, that has to do with that expression, the one that we were talking about. Here is the value of G that I was making a big fuss over, okay? That is the expression, the value for G. Wait a minute. G is actually has units. Okay. So it's talking 1 kilogram and 1 meter. So it has units. This is the value of G with units. Okay. The units and the value was chosen to match with that of the apple. Okay. And this is the force expressed in terms of this value. Okay. So this G, 6.67 10 to the negative 11 Newton meter squared per kilogram squared is a property of our own universe. It's unique to us. Okay, we talked about the weight and weightlessness. Let me see quickly. This is basically the project that I was hoping some of you will take it. This actually has more to say about it than this one. Actually, Einstein, when he looked to this one, he was basically perplexed about it that, look, the only force known that it's going to cancel its effect when it's applied is the force of gravity. And that's why he invented actually the general theory of relativity going back to this model, okay? But I hope you guys understand, but if you move up, in this case, if you accelerate, then there is more force on you downward in here, okay? You can do this experiment at home. Let me quickly scan these things in here. The projectile motion is an example, basically, of a motion in the horizontal direction and the vertical direction, and that's what I called earlier motion in 2 dimensions. And the path is actually a parabola, okay? Parabola, that's the path of it, which is one of the conic shapes. The conic shapes are ellipse, parabola, a sphere, and actually the hyperbola. Okay, those are the shapes. The sphere and the ellipse, they're related to one another. Again, this is how the projectile works. Okay, one of the key concepts of the parabola, actually, for the projectile motion is the altitude and the range, okay? A 15-degree angle and a 75-degree angle, they add up to 90 degree. They have the same range, but they have different altitudes, okay? A 30-degree angle and a 60-degree angle have the same range. They reach the same point, but they have different altitudes again. And the 45-degree angle can be only added up to itself, 45-degree angle. And that is the maximum range you're going to get. So this is a typical question you're going to see probably on some of the shows and things like that. The range is at max at 45 degrees, provided the air resistance and the humidity are negligible. If they are, then the angle is actually different than this one. It's slightly less. So if you are in the military or planning to go into the military and you're going to play with cannons, you have to take that into account, and you will have to discard to go slightly less than 45 degrees. Okay, here is the effects of the air resistance again. So it's going to be, otherwise, the acceleration is going to be g, okay? An object is put into orbit if it reaches a certain velocity. So at some point, if you are on one of the moons of Mars, for example, you can easily put an object into orbit just by throwing it, because the force there is not high enough. Let me get into a couple of points that I think. Here is the activity I was talking about for you guys, the ellipse, okay? So this is similar to this one, so you can see this one and basically do it. When you're doing this one at home, make sure that you don't poke yourself with this thumbtacks, okay? Because there sometimes can be very dangerous. What I do is I bring a card box and put it underneath the paper and use that to stick the experiment to do it with it, okay? So again, the speed with which you need to reach in order to reach the orbital speed, which brings me to the last thing in here, which is the escape velocity. I mentioned that to be 11.2 kilometers per second. So this is in a nutshell your chapter. I hope that you guys can finish this concept, read, go through them. And if you have any questions, please do ask, okay? So we have 3 questions for the day today. First one is C. The second one, was it C? The first one? I forgot even what... no, it was not C.
It was B.
B, okay. The second one is 25 centimeters, 0.25 meters. And the third one is A, mass or distance. See you guys Thursday. Enjoy
I have a
your...
question. I'm sorry.
Yes, sir. Go ahead, sir.
Okay, I was wondering, the quiz that you had posted, I just want to make sure it's only for chapters 1 and 2.
Yes, okay. And there will be another quiz, okay, by the end of this week.
Okay, sounds good. Thank you.
It's going to be due a week from today. Any other questions?
Will the PowerPoint be left up for us to review?
It's not online?
I don't know. I'm just asking.
I think it's online already. Okay, Sarah thinks that it's online. So I think it's on Canvas, yes. It has been on Canvas since I think a few days ago. Okay, see you guys. Be safe. Don't go in where crowds are. Try to avoid them. It's going to be super hot, so stay cool also.
Professor, I have a quick question regarding
Yeah.
the quiz. For the quiz, do we have to download a certain program, correct?
I think it works best with Chrome. That's what they asked. Chrome, yes. Browser.
And what is it do? Because I haven't really clicked on it. I'm gonna work on my quiz today. But what exactly does it consist of? Like, as far as the
security, yeah. What it wants you to do is to agree to the fact that your screen is going to be recorded, not your face, your screen, your.
Got it.
Okay, what you're typing in there, okay, and that you're going to be sitting in the session, not leave it. The minute you leave it, it's going to be submitted, and you cannot open any other browser. And the fact that your memory of your browser also will be, the cache of the browser will be cleared, because some people, in the past, not in your class, in other places, what they do, they open the review materials or whatever they have open, and they go back to it, and it's still in memory, it's still in the cache of the browser. So basically trying to defeat the purpose, trying to cheat, if you wish. So this was done for everybody, that, okay, we're going to clear the cache so that if you go back to the history, you're not going to see these things and that was in there. So there were all kinds of people trying to trick systems, basically trying to cheat. And of course, that's not good. Yeah.
Okay, sounds good.
But there is no camera requirement. I'm sorry, in the sense that it's not going to record your face. So be at ease with that. Relax, but take the time into the quiz. Okay.
Okay, sounds good. Thank you.
Okay, no problem. Any other question? Okay. See you guys on Tuesday. I'm sorry, at 8:30 in the morning. Bye.
Okay, bye. Thank you.
Okay, bye.